So welcome back. Happy Friday. Today is our 37th class of the semester. We are covering modeling using exponential functions. You recall modeling just means we're doing word problems. We've got applications in store, and we're going to try to come up with appropriate equations that will model those applications. Next class on Monday, we've got another modeling day, except instead of doing exponential stuff, we'll do log stuff. That's Monday. And then Wednesday is the very last day of new stuff for our course this semester. We're going to do some data fitting. You can see the last 2 days of our course says TBA and review day. Assuming there's no snow day, we will have 2 review days coming up, Friday and Monday. Final exam is a week from this coming Wednesday. Questions on the calendar? I'm going to hand you the quiz on the 14th, and you'll turn it back in to me on the 16th. Yeah. Also, project number 4, I think you have all the tools that you need to answer all the questions on project 4. And so if you've got some time this weekend and you want to get that out of the way, it might be better than waiting until it's actually due to do it. Okay. So on this page right here, you had some data. What did you guys think? Linear, logarithmic, or exponential? Yeah, all right, so I mean, if we're drawing something that kind of grows slow in the beginning and then faster, 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 that's exponential. That looks good. Log graphs typically look like this. This is y equals log x, something like that. And this one here might be, y equals like 5 to the x or so. Linear, what do you think about linear? Yeah, maybe something like that. I mean, it's okay. It's better than log, but the data looks exponential-ish to me. It's hard to know. Let's take a look at the demo. Here at the bottom of the page, there's just a lot of factual information. We're not going to read through it right now, but you might reference it while you're doing the activity. So there's like lots of stuff with formulas and definitions right here. We're just going to jump in and start doing some problems. So let's try number 2 on this next page. On September 13, 2014, there were an estimated 3,902 Ebola cases recorded in West Africa, specifically these 3 countries here, Guinea, Liberia, and Sierra Leone. Between that date, September 3rd, and November 18th, the number of Ebola cases grew at a continuous growth rate of 1.252% per day. 1.252% per day, and it's continuous. Okay, and it says construct 2 equivalent models for this outbreak between September 3rd and November 18th. What we're looking for is a formula that will maybe help us predict, on September 18th, this is roughly how many Ebola cases we might have expected, and on October 3rd, it's roughly this. We just want an equation that we can plug in and see if we can model the given information. Now, there is one keyword that we got to focus on, and is right there. If you see the word continuous, all right, take a step back. This is growing at a percentage, a constant percentage. Is that a linear thing or an exponential thing? That's an exponential thing. A linear thing would be growing at a constant number, a constant amount every day. Like 2 new people every day would be linear. But this is a constant percentage, so that is an exponential. And if you see the word continuous, then that differentiates one version of exponentials from all the other versions. So I'm going to write up here, I don't remember exactly what our letters were, but maybe we had a formula like that. It was a P0, maybe it was A. A? This one? Yeah, I mean the letters change depending on the book and the notes. Okay, and then we had this other guy, P0E to the KT, where E is that magic number, it's about 2.7. And so on the one hand, if I'm using this formula here, it feels like, hey, maybe B is, I can just copy, well, almost copy. What would you put there for B if the rate was 1.252%? 1.01252, that's it. You guys remember that the B number there is always 1 plus the rate. You never get to put that rate as a percentage. You always have to make it a decimal. Okay, but on the other hand, we've got this K up here, and maybe it's actually K is just the 0.01252. No 1 plus in the E to the K version. It's just you copy the rate, slap it up there next to a T, and it's done. So that word that I circled there, continuous, tells us definitively it's one or the other. And you got to get it right. The word continuous means E. And we talked about this a little bit when we defined the exponential growth functions. The word continuous means you are using the E formula. So that means we've got to grab that second formula. So here it is. P equals, why don't I be really explicit here? P of T equals, okay, P0, how much is it in this example? 3,902. It's always the initial amount. I'm copying the second formula. We'll highlight it in yellow here. Whoa. Ooh. I'll highlight it in yellow there. Okay, E is just E. K is the percentage. It's this 0.01252. T is T. So that's it. That's the formula that will approximate how many cases of Ebola happened at any moment in time, T. You want to know 5 days after the start of this experiment, just plug in T equals 5 and you'll get a number of Ebola cases. 40 days in, just plug in T equals 40, okay? So two things to be aware of. Like I said, you see that word continuous, it is for sure the E formula. That's the definition of that word continuous. And the other thing to be aware of is that if we were doing the B formula, you got to do 1 plus. But if you're doing the E formula, there's no 1 plus. It's just that rate gets copied, okay? That's right. If it doesn't say continuous, you're using the B formula. Yeah. Yeah, Jed. Yes. Yeah. I mean, that word just makes it one or the other. Okay. All right. So this is fine, but maybe we really want it for some reason to be in the other formula. And so what we're going to do is try to convert this thing into a formula like the other one that we've seen. Now, I think we've done this once before. We're not going to build it from scratch here. I'm just going to point to our reference sheet. You take a look here. This is the B formula that we were just talking about. And if you happen to know the K, how much was K in our example? 0.01252, that's the K. If you happen to know the K and you want to find B, there's your formula. B equals E to the whatever K is. So that's all we're going to do in order to convert to the other formula up here. B equals E to the K. I'm hoping it doesn't look like magic. If you think about it a little bit, you'll see why that's true. I'm pretty sure we've done it in a previous class. So we're just going to use the formula here. E to the 0.01252. And now we need somebody with a calculator to type that in for us. Okay. So that's the value of B, which means we can then use the first formula, now highlighted in blue, and get an equivalent version of this. So first formula, P of T equals, initial population is still, initial pop, 3902. We've just discovered that B is 1.01259, this thing from the calculator, 3902 times 1.01259. Again, the blue formula raised to the T. And that's it. That's the other formula that we could use. You'll notice that the B that I originally wrote down in blue is wrong. Is it really wrong? It's not all that wrong, right? I mean, it's close. So the difference between continuous and daily is not that big, and you can see it didn't have much of an impact on the right answer compared to like the obvious wrong answer. But still, we got to make sure we're using the formulas in the right way. Okay. So again, word continuous says you are in E land. Without that word, you're just in the B land. Okay. you'll have opportunity to practice this in the activity. And I just want to show you something real quick. You don't need to do it on your calculator. But if I were to come in here, and I'm going to graph the first formula, y equals, so 3902 times e to the 0.01252. I can't use t, I'm using x. So that's one equation. And then the other equation we're going to do is this 3902, it's this guy over here, times. Okay, instead of typing in this 1.01259, which had some rounding in it, right? Like Jamie didn't share all the digits that he had on the calculator. How did we get this number? We did e to this thing, right? Okay, so I'm gonna put that here. I'll just type it in parentheses. So e to the this guy, 0.01252. So it's e to that thing. So that's this guy, and then I'll raise it to the t. So raised to the x. Okay. All right. Before we graph, first thing I'm going to do is turn this one off so it is not highlighted. It's just going to be the first graph. And then I'm going to think about my window. Let's look between like 0 and 100 days, for example. And go every 10 days. And then let's see, a y min. All right, so we're never going to get fewer than 0 people. How many people are infected at the start? Yeah, almost 4,000. And is the number of people shrinking or growing? It's growing, so I got to put something that's at least, 4,000. I don't know what it's going to be. I'll put 8,000 here, and then we can see what happens. Go by thousands, maybe. Okay, so here's the graph. So the fact that this graph shot off the top of the screen, what does that mean about my y max? It was too low, right? I didn't capture everything. I was trying to look at 100 days, and we shot off the screen here. So apparently 8,000 didn't cut it. About 20,000. All right. 20,000 was maybe a little bit too high, right? We shot off the right side of the screen, but this is okay. All right, so now that was the graph of this first guy. So I'm now going to graph the second guy, but I'm going to arrow over here and hit enter, which is going to make that thick. So it's going to graph the second one thick. If we have done this right and this thing is equivalent to this thing, then what are we expecting to see? The same thing. And that's why I wanted to make it thick, because if you don't make it thick, what are you going to see? Nothing, because it's just going to graph exactly on top of the same thing it graphed before. Okay, so that's the idea. Two different ways to say the same thing. Okay, coming down here, it says November 18 represents day 83. 83 days from when? Yeah, from the outbreak, from September 3rd. So that's just them being nice, so we don't have to count, the 83 days. Then it says, how many Ebola cases does this model predict for December 5th? So what do we need to count now? Yeah, from the 18th, we need to count over to December 5th. Okay, so I guess you could count on your fingers if you want. It's not that big a number, right? Maybe we'll be a little bit more high powered than that. How many days in November? 30 days in November. So then how far from? Yes, that's 12 days counting the 19th to the yeah, to the start of December, and then another 5 there, right? So that's 17 more days. It's 17 days past this to get to this. So 17 days past this number is 100. Okay, well that's convenient. But anyway, you gotta go through the calculation. Okay, so that means we are doing P of 100, 100 days in. P of 100. 3902. I'm doing this first orange formula. E to the 0.01252 times 100. That is what we're after. And that is what we type in the calculator. But what I promised you was that the first orange formula and the second orange formula both represented exactly the same thing. So what's another way to do this? How much is T now? Okay. Right, that's the second orange formula. And what we said was that there were just two different ways to say exactly the same thing. So we should get the same answer here. So let's show you on the calculator here. Okay, so the first one, 3902 times e to the 0.01252 times 100. So 13,646 and change. That's 100 days in. Compared to, we can type this version of things, 3902 times 1.01259 raised to the 100. What's your expectation? Should be the same, right? Because we said it's the same phenomenon. How far off? Is it just 0.3 off? Look carefully. No, look carefully. You're not in the right. You're making me censor my video. I'm putting this on YouTube here. How far off are we? There's 12 people. Somebody said rounding. This is rounding. That is rounding error. And like 12 people is a significant amount of rounding error, right? So that's why I was saying like it's okay to write this. But you'll notice that when I typed in here y equals, I didn't write that, right? Okay, so then maybe better would be to get a few more digits. How about we try this one other way? E to the, I'm typing this guy right here just to get that number. E to the 0.01252, that number, okay? Now I'm going to type in this second orange formula, 3902 times, but then instead of retyping this, I'm just going to do second answer. Fair? That's this number, and then it's this number in parentheses, and then raised to the 100th power. Okay, remember the right answer was way up here at the top, 13,646, 58411, 13,646, 58411, right? Yeah, Pete. I think that the scientific calculators pretty much have that standard, so I'm happy to show you on yours if you have one. Yeah. Okay. All right, so that's that guy. Let's talk a tiny bit about half-life stuff. Okay, so there's a lot of words here. We're not going to read through all of them. Let's just do some highlights. Carbon-14 is a radioactive element. As such, it decays over time. So like right now, all of us have a certain amount of carbon-14 in our bones. And as long as we are alive, that pretty much stays constant. But as soon as we pass away, the amount of carbon-14 we have decays. Slowly, slowly, slowly changes into something else. I don't know my chemistry. Anybody know what it changes? Like it converts from, what is it? It converts from carbon-14 to carbon-12? Okay, so it converts from one thing to another, and this is something that like we have machines that can detect, you know, like what percentage of the carbon in you is still carbon-14 versus what percentage has slowly switched over into carbon-12, okay? And so the fact is that this decay from carbon-14 while you're alive to carbon-12 when you pass away happens incredibly slowly, to the tune of, it takes about 5,730 years for half of the carbon-14 to switch over into carbon-12, okay? For half. So suppose that you have a dinosaur bone, and you measure the carbon in it, and you discover that exactly half of the carbon is carbon-14 still, and half of it is carbon-12. How old is this dinosaur bone? It's 5,730 years, because exactly half has switched from one to the other, right? Okay, so that's not realistic. I don't believe there were dinosaurs. I'm not going to try to get into like that whole thing, but I don't think there were dinosaurs on Earth 5,700 years ago. I think it was longer. And so, if we, let's suppose that we go another 5,730 years. So we were half carbon-14, and now if we go half again, we're at a quarter of what we started with, right? Well, if you're at a quarter here, then what must be on the other side with carbon-12? Must be 3/4. Machine can tell you whether, you know, if it's a quarter and 3/4. So how many years has it been in that case? It's got to be 2 of those 5,700 years, right? So like roughly. Right, and so like just looking at this ratio of how much is still carbon-12 and how much is carbon-14, we can decide how many half-lives have passed, how many multiples of this 5,700 years have passed, okay? All right, so let's take a look at this formula right here. Suppose that the amount of carbon-14 present T years after we start this experiment is given by this formula, 100 times A to the T. Initially, we're just going to pretend we have 100 grams of this stuff in the bone that we are studying, 100 times A to the T. Okay, and the goal is to find A. We want to build it so that whatever A we calculate, it's going to make it so half of that stuff disappears every 5,730 years, okay? So let's give it a shot. If half of it is going to disappear, that means that if I plug 5,730 in for T, then how much should I have left over if I started with 100? So we better have 50 grams of that stuff left over, right? And so here's the equation that we're going to solve. It's 100A to the 5,730 equals 50. We buy it? 5,730 years in, you have half left over. Okay, we can solve this equation. First, we're going to divide by 100. A to the 5,730 equals 50 over 100, which simplifies, so let's do that. That's just a half. Okay, that makes sense because we have half after 5,730 years. How do we solve that equation? Is it log of both sides to solve this? Maybe a natural log to solve that? The reason we use logs to solve equations is when the variable is in the exponent. Is the variable in the exponent in that equation? No, logs are not the right tool. Yeah, that's what we're going to do because we've got our number raised to the 5,730th power. So we need to do the opposite of that, right? And the opposite of raising something to the 5,730th power is to take the 5,730th root, which is kind of a mind-blowing thing to think about. So maybe easier would be to raise this side to 1 over 5,730, because what do you do with those powers? You multiply and therefore they cancel. That's the goal, but you can't just go around doing that on one side without doing it on the other side as well, okay? Okay, so that means on the left-hand side, we just get A, and on the right-hand side, we get 1/2 to the 1 over 5,730. Now you could type that on the calculator if you want to. It is going to be an absurdly small number. You know, like, anybody have, I don't even know what the calculator is going to think about this thing. What does it say? How many 9s you got?
3, 9, 8, 5.
Jed, you got something different? Actually, I like this number. Anybody have we have a third vote?
Yeah, I got 9 here.
Lots of 9s? Yep. Okay. All right. So why is it so close to 1? Well, it's if something is decaying really, really slowly, then maybe like a year from now, you have 99.99% of what you had now. And then a year later, you have again another 99.99%. And it's going to gradually disappear, but it's going to take forever and a day to get there. I'm not super interested in the 0.999, but I do want to point out something going on here with this A value, 1/2, because it was a half-life. 5,730, what was that? That was the number of years to get cut in half, 5,730. And it's always just going to be 1 over whatever that number of years is. And so if I just kind of put this back into my formula here, we get 100 times, we've discovered A is that number right there, the 1/2 to the 1 over 5,730. But it is still being raised to the T. I'm going to circle A there, A there. Still raised to the T, right? Looks complicated, but it's the same 100A to the T. And the last thing we're doing here in order to get a formula that's on the next page is what can you do with these powers? We can still multiply them. So that means that this guy is equal to 100 times 1/2 to the, when you multiply these fractions, what do you get? put them together. So how do we get a single fraction there? This is t over 1 if you want. Straight across. T over 5730. And by that? So that right there is our formula that tells you how much stuff you have at any moment in time. 1/2 to the t over 5730. And it's always going to be that. 1/2 to the t over however long it takes. So all of that was to just build this formula, which you are ultimately going to use, which is on the very next page. So we just built this thing here. Thank you. Okay. So let's give this a shot. Number 4, the burial cloth of an Egyptian mummy is estimated to contain 59% of the carbon-14 it contained originally. How long ago was the mummy buried? Okay, so this is exactly the kind of problem that our brand new formula is going to help us solve. Before we use any fancy formula, is the answer to this question, remember the question is how long ago was the mummy buried? Is the answer to this question more or less than 5,730 years? Few votes for less. Other votes. Did this mummy die more or less than 5,730 years ago? All we know is that 59% of the carbon-14 is still there. It's less because we haven't gotten down to 50%, right? We're still slowly approaching 50%. So it's going to be close to 5,730 years, but it's going to be less than 5,730. And now we'll use this brand new formula here to solve. M of t equals m sub 0. That's the initial amount of carbon-14. In this case, it says 59% is still there. So if we're thinking percentages, then what do you want to put for the initial amount? How much? 100%, but we never write percentages inside of equations. We convert 100% into what number? 1. There we go. 1 is our initial amount. That's 100%. Times rest of the formula, 1/2 to the t over h. Always 1/2 for any half-life problem. T is just t divided by h. H is defined up here. It says it's the substance's half-life. What is the half-life for carbon-14? 5,730. So that formula right there tells us how much carbon-14 should still be in the mummy at any moment in time. But the one moment in time we're focused on is when what percentage of the carbon-14 is there? 59. So where is that 59% going? Is it the t? Is it the m of t? It's the m of t. It's the output. T is time. We want to know the time, but we have the output. The amount of carbon-14 is 59%. Now I made an error in the equation that I just wrote down. What about the t-value? No, 59 is not the t. 59 is the output. But it's 0.59. Again, you're not putting the percentage as a percentage. You got to put it as a decimal. 0.59 is good. Okay. When we solve this equation, we're going to have an answer t equals. That's great because that's what the question is asking for. How long? What is t? Okay, to decide how to solve it, we just need to look where the variable is. Where is it? It's in the exponent. What's the right tool when the variable is in the exponent? Is logs. This guy is logs. So we'll take the log of both sides. Log of 0.59 equals log of, I won't write the 1 anymore, 1/2 to the t over 5730. Okay, now what?
So it's t log 1/2 kind of stuff.
I think yeah, the t is coming down to the front, right? The whole exponent is coming down to the front. So I'm copying everything else, but just bringing the exponent down. Log of 0.59 equals the whole exponent comes in front. That's a log property. Okay, for those of us that are not super comfortable with logs, that equation might be intimidating, but the fact is log of 0.59 is just a number. It's going to come out on the calculator in a second. Log of a half is just a number on the calculator. So this is just a bunch of numbers floating around. All I got to do is focus on t. So how do I move the 5730? Multiply it. How do I move the log of half? Divide. So just put them in the right spots. 5730 gets multiplied by the log of 0.59. And the log of a half goes underneath. That's it. Okay, so I think I've typed this correctly. 5730 log of 0.59 over log of a half. We expected it was going to be less than 5,730 years, but pretty close to 5,730. That number is quite reasonable, 4,360, say 62. $43.62. Okay. And this is actually how we figure out how things that are really old, how old they are. Because otherwise it's just like, you know, a bone. Like what do you do with this bone? How can you measure? Like it just looks, everything looks old at a certain point, right? And when we're talking 5,000 years ago or a few 100,000 years ago, right? Maybe a few million years ago, it's like, how can you tell? Well, we have the ability to measure carbon-14, and armed with only that machine, whatever that machine is, and some college algebra, we can find out how old this stuff is. Okay, one more question here about the mummy. It says, find the continuous decay rate. You guys remember continuous means what magic letter is E. So the word continuous says there's an E thing happening. So up at the top of this page, we didn't talk about it, but up here in green is the E version of the formula. And there's a letter R, which we have not seen in here, but there it is. Turns out to be ln of 2 divided by h, same h as before. So all we have to do is crunch through that magic formula, and we will have our answer. So R is equal to ln of 2 divided by h. What is h in this example? 5730. Somebody with a calculator type that in for us. Somebody's going to have to jump in because I'm. What does it say at the end? E to the -4. Perfect. I'll read again. Is it 1059? Trevor, what do you have? 1, 2. Anybody? A little more? Yes. Okay, good. So that is the continuous decay rate. That's a decimal. To bring it back to a percentage, just for comparison's sake, the decimal point goes 2 to the right. So as a percentage, it's 0.012%, about 0.01%. Every year, about 0.01% of the carbon decays, which is great because otherwise it would disappear so fast that we wouldn't have the ability to measure it. There'd be so little left that we couldn't measure it. Okay, so then if we just grab that other formula that was at the top there, it said m of t equals, I'll just write it here, m0e to the negative RT. And now we're just going to copy the stuff from our problem. M sub 0 is still the initial amount. What is the initial amount? 1 is what we're calling it, 100%. We just call it 1 as a default. E to the negative R, we just discovered, there's your R, 0.00012, that's good enough. Raised to the T. Oh, as I read this question more carefully, I see that this was the answer they were after. The continuous decay rate is just that number. We wrote down the follow-up formula. Okay, so there's a few new formulas for today. You got them all there. You can write them on your reference sheet before the final exam. It's just going to be about practicing with these formulas. One last thing here, and then you'll jump into the activities. Exponential functions, when they're growing, how high do they get? Infinite, which is not realistic for the number of cases of Ebola or for the number of ladybugs in a field, because there's like finite resources, right? Like at some point you are bigger than is even possible. And so maybe a more realistic thing would be like in this blue curve, that kind of looks maybe exponential to me. But at some point, the amount of resources for these ladybugs in the field starts to decrease. Or maybe the number of predators increases. Hey, there's a great field with ladybugs in there. Let's go get lunch. And so at some point, this exponential growth thing maybe turns into a, yeah, still increasing, but not as rapidly as it was before. And maybe just kind of leveling off at something that we might call the capacity of the field for the ladybugs, right? Like you can't get past a certain number of ladybugs in a field. There just isn't enough food and water and all that stuff for the ladybugs to continue to grow. And so this much more complicated behavior is called logistic growth. Logistic growth. Because it's more complicated, of course, it has a more complicated equation. It's not just e to the RT. It's something more complicated. C is a constant, so is A, so is B. I don't know that I'll ask you to do very much with it, but I just want you to see like a logistic thing that's more reasonable, more realistic in the long term than anything that we've talked about, because they grow to infinity. Okay, the activity starts on the next page. Let's see how far we can get.